So today we're going to talk about a brief history of light. Since the dawn of time, up until Sir Isaac Newton, there were two theories that existed as to what the nature of the light was. One was that the objects shot out these little bundles of light or emitted these corpuscles of light that entered the eye. So picture everything that you're looking at is shooting these little bundles and they're coming into your eyes and your eyes are reading those little bundles. Well, the second idea, which is not necessarily any crazier, is that your eyes emit these rays and the rays reflect off of the object, and that's what allows you to see, is because the eyes like kind of like picture Superman with the X-ray vision and the laser vision. So one of those two things, either the objects are emitting these corpuscles or your eyes are emitting these rays and your rays are catching those back again. So we get up to Sir Isaac Newton, and few people know or knew that he loved optics. Optics was one of his favorite things to study. So Newton systematically studied light. He would pass a prism through the sunlight through a prism, and he observed the band of colors that would come out of it, to where we would get this nice little rainbow, kind of like you've probably done on your own. So he concluded that light was made up of these really, really small particles that were traveling at really, really fast speeds. So kind of think through that. Sort of matches that whole corpuscle idea, the like these little bundles of light. And this explains why light would travel in a very straight line, because it's traveling so fast, and why it would cast such sharp shadows. So you think through, like, if we have a wave property that's called diffraction, which is the bending of a wave around a barrier, if it's traveling that fast, it's not going to diffract nearly as much because of the speed that it's traveling at. The problem with that is, why don't the particles collide whenever they interact with each other? So for instance, if I take a flashlight here and I shoot the light this way, and I take another flashlight here and shoot the light this way, as those light beams come towards each other and those bundles of light hit each other, then we should end up with an explosion of color all over the room, kind of like a dance revolution, right? The other question then is, we don't, though. That's the problem. And so we end up with this sort of interference that we talked about earlier, where the light waves just really literally travel through each other. So the next question then is, why would one color of particle be bent more than the other? So why does the red light get bent? Why does the blue light get bent? And why don't they get bent the same if these are these different particles? Another guy comes along. He lives about the same time as Sir Isaac Newton. His name was Christian Huygens. And he suggests that light is actually made of these small waves instead of particles, because then it matches that sort of interference. It matches sort of the problem with the red and the blue light bending. And the answer to this begs more questions, though. But if it is a wave, then why can't light diffract around the corners? Why can't it go around obstacles? And then why can light travel in a vacuum? Because now you think through, in the 1600s, the only type of wave that they really understood was that longitudinal wave. And in a longitudinal wave needs a medium, which is like your sound wave, the air that my voice is making the sound wave in the air, going to the microphones, coming out of you from the video, and that's that longitudinal wave. Now, if I sucked all the air out of the room, you wouldn't be able to hear me, or out the air out of your room, you wouldn't be able to hear me either, because there's no medium there. And so the problem with this wave is that they didn't understand there's this other kind of wave called a transverse wave that does not need a medium. So they're questioning, like, well, how can it travel through a vacuum if it's a wave? So for 100 years, this argument went back and forth, Newton versus Huygens, or particle versus wave, and along comes a guy named Thomas Young in 1801. So he passes a beam of light through two closely spaced holes, and the light diffracted, demonstrating that light is more wave-like. So this should look familiar to you. It was similar to the ripple tank that we did. So he put it so that there's this one little gap here, and we get this one point source of these waves coming through. And you can picture it as like the red being the trough, the yellow being the crest. And then he made another gap where he has these two, and we end up with these 2 point sources. It's very similar to what we did with the ripple tank, similar to what I showed you on the overhead projector. And what he ended up with this really light area in the middle. We have these really dark fringes on the sides, and then more light areas and then dark areas. And he discovered that those are where the constructive and destructive interference is happening. So we have the light area where the constructive interference is happening, and the destructive interference is where the dark area is happening. And so he concludes, because this has more wave-like properties, that it is more like a wave. But then they had to come up with some explanations. So since space is empty, there had to be something else that the light could travel through. And so they came up with this idea, what they called ether. And they said that ether is everywhere that it has to have the properties of steel because light travels so fast, and the ether has to be super dense so the light can travel that fast through it. And then anything can move, but even though it's super dense, anything can move through it with greatest ease. So it has to be everywhere because light is everywhere. It has to be more dense than steel because light travels so quickly. But even though it travels quickly, it has to be able to get through it super, super easily. So now we have to test, does ether exist? And the interesting part to this is we have to be able to measure the speed of light. And so this is the beginning of us being able to come up with something that measures the speed of light. So if Earth has this ether around it, then the Earth must cause these ether waves as it travels through it. So picture if I take a beach ball and I'm in a pool and I drag the beach ball through the pool, isn't it going to create these waves around it? And that's similar to what the Earth would be doing to the ether as it's plowing through space. Light going with the ether then would have to be going faster because it's compressing those waves together, and light going across the waves would have to be going the same velocity. So you could kind of picture like if the Earth is here and it's moving this way and we get these waves that are being spread out in the back there, then if I shoot light this way, it's going to have a very different speed than if I shoot light this way or if I shoot light to the sides. So that's why we have to be able to measure the speed of light, because if we can shoot light in all of those different directions, then we can determine if it's all traveling at the same speed, then there is no such thing as ether. And that's where Michelson and Morley come in. In 1887, they developed what was called an interferometer, and it measures the speed of those waves. So you can picture this was the original optical device that they used. So they send this incoming light here. They shoot it. It hits this sort of half silvered mirror. So some of the light comes through, hits a mirror and reflects and comes back again. Some of the light comes up here, hits this mirror and comes back again. And then there's this interference pattern down here. And if they interfere correctly, then it would show that the speed of light is the same no matter what, because you think through that this one here might be traveling this way on the Earth, but this one here is traveling this way on the Earth. So one of them will get affected by the ether waves and one of them won't get affected by the ether waves. And guess what it showed? It showed that the speed of light doesn't change, which means what about ether? Yeah, it means that ether doesn't exist either. So we had to come up with a new theory to explain this then. And through a couple of different iterations, we end up with this theory that we have now. The current theory says that light is caused by electricity and magnetism combined. Because of its particle nature, it can travel through a vacuum. So we end up with, if you picture, these guys here are creating a magnetic wave that caused the wave to be able to go this way. These guys here are creating an electric wave, words elude me today, an electric wave that causes it to be able to go this way. And it's that combination of the up and down magnetic wave and the side to side electric wave that creates a light wave. It's an electromagnetic wave. So you kind of, if you can do this, it can help you remember that we have the back and forth and the up and down together. That's what creates an electromagnetic wave. And then the sky became the limit, because now that we know what a light wave is, we can adjust both of these to end up with light waves in any part of the spectrum and start saying, well, what can we do with light that's in that spectrum? Oh, this is a low wave, big wavelength, low frequency, super great for communication. That'd be great television or great radio. You know, this is a really high frequency, low, did I say that last one wrong? Long wavelength, short frequency is television. A very short wavelength, high frequency, that's going to be something more like where you are doing ultraviolet, or maybe you are doing X-rays, something that is invasive and getting into your body. So we can study all those different parts of the electromagnetic spectrum now then. So we end up saying that neither one of them was really correct. In fact, both of them were really correct. That light is a wave and light is a particle, and it exists as both at the same time. And that's what we would call the wave-particle duality. So light exists as both a wave and a particle at the same time. It shows itself however you're looking for it, though. So if you experiment If in your experiment you look at light as a particle and you try and prove that it's a particle, then it will behave like a particle. But in your experiment, if you're proving that light is a wave, then it will behave like a wave in that way. So it is both at the same time, wave-particle duality. This is a video that I picked up a long time ago from Dr. Quantum. I'll put the link there that you can look at it later. Or you can Google it, Dr. Quantum video, and it kind of walks through that, like the history of what that is and how that looks in sort of a cute animation for that. So lastly then, what do you see in this? Is light a wave or a particle? And the answer is yes. Can you see how it's both? Where we have W here, A here, V here, and E here, right? Or can you see that this is P A R T I C L E, right? So can you see both of those now? Light is both a wave and a particle. And that is a brief history of light.